Hello everyone, my name is Ajay Meddi from Aeronautical Engineering. In this presentation, I am going to discuss about array and data structure, algorithms and data structures for new model of computation. Abstract. In the early days of computer science, the community settled on a simple standard model of computing and a basic canon of general purpose algorithms and data structures suited to that model. With isochronous computing, heterogeneous multiprocessors, flash memory, energy aware computing, cache and other antitropic memory, distributed computing, streaming environments, functional languages, graphic coprocessors, etc. The basic canon of algorithms and data structures is not enough. Software developer know of real-world constraints and new models of computation and use them to design effective algorithms and data structures. These constraints motivate the development of elegant algorithms with broad utility. As examples, we present four algorithms that were motivated by specific hardware nonsense but are generally useful. Reservoir sampling, majority of a stream, b-heap and compacting an array in log n time, standard model and canon. In the early days of computer science, the community settled on a simple standard model of computing and a basic canon of general purpose algorithms and data structures. The standard model of computing has following. First one processor that performs a single instruction at a time. Second one, copious memory that is uniformly accessible with negligible latency. Third one, readily available persistent storage with significant latency. Fourth one, input and output that is insensitive to content or context and others of magnitude slower. Fifth one, resources and connections that do not change. Sixth one, no significant concerns about energy use or component failure, permanent or intermittent. The canon of data structures and algorithms include list, quicksort, Boyer-Moray, string search, trees and hash tables. Knuth even began what was intended to be a complete encyclopedia of computing, although new and better so. The canon of data structures and algorithms include list, quicksort, Boyer-Moray, string search, trees and hash tables. Knuth even began what was intended to be a complete encyclopedia of computing, regularly sent to the editors of the Dictionary of Algorithm and Data Structures. None has been both new and widely applicable. The most recent general purpose data structure is the skip list, which was invented in 1989. Work continues in specialized areas such as graphics, distributed systems, user interaction, cyber physical systems, and artificial intelligence. Except perhaps for quantum computing algorithms, general textbooks have the same model and cover similar. New models. Programmers will not be prepared for modern systems with only this background. Few actual computers match the standard model in all accepts. Although hardware caching and system support well approximate the standard model, developers must be aware of constraints and ideal scenarios of the software's execution environment. New constraints of time, space, energy, and hardware motivate new ways of thinking and lead programmers to need new approaches to old problems. So many advances have been made in the hardware and systems that slavishly staying with that standard model of forgives much performance. Exciting advantages are available to explode in isochronous computing, heterogeneous multiprocessors, flash memory, energy aware computing, cache and other anisotropic memory, distributed computing, graphics coprocessors, networks of many simple devices, and streaming environments. In some cases, there are enormously waste in maintaining or staying with the standard computing model. In other cases, additional resources are squared if used without regard to their particular strengths and weakness. For example, flash memory is used in solid state drives and memory cards for cameras and smartphones wear out. Individual bits in flash memory can be set, but bits can only be cleared by erasing an entire block of memory. Blocks of memory can only be erased up to 100,000 times before excessive errors occur. The entire block of memory then become unusable. To extend their usable life, many flash memory subsystems use sophisticated algorithms to spread writes throughout the memory and still maintain the abstraction of persistent memory that is intensive to write locations. This is often accomplished through generalizing file system or log structured file systems whose of writes match flash memories well. Example algorithm and data structures. In this session, we give four instances of elegant, generally useful algorithms and data structures that were developed for particular circumstances but are not widely known. They illustrate the opportunity to create new algorithms and data structures motivated by new computing constraints. Reservoir sampling. For the first algorithm, consider a stream environment, that is, items arrive on at a time. The program does not know how many items will arrive or equivalently. An answer may be secured may be required after a unspecified number of items has arrived. Since we do not know how many items there will be, we limit resources to be a constant amount of memory. Place a counter that requires long n bytes. As a real world example, imagine a network of tiny sensors detecting pollution. Randomly, a sample is requested from every sensor in the network. The tiny sensors cannot store many samples, and for statistical purposes, all samples must be equally likely. The challenge is to choose one of the items randomly, with all items having an equal chance of being chosen. If the number of items is known beforehand, one could generate a random number of in the range of the number of items. Alternatively, one can store all the items, possibly in some data structure that can grow as needed, and choose one who when needed. Neither of these standard solutions satisfies the constraint of not knowing the number of items beforehand. A simple solution is attributed to Waterman. It requires storing the item chosen so far and a counter n that holds the number of items from the stream so far. To begin, store the first item and set n to 1. For each new item, replace the chosen item by the new item with probability 1 is equal to do n row 1p and increment n. The proof the proof of algorithm correctness is simple too. Clearly, we end up with one of the items, but does every item have an equal chance of being chosen? We sketch an induction proof. The first item is kept as the chosen item after the first step with a chance of 1 equal to 1, which is correct. The second item is kept with a probability of 1 is equal to 2. So neither item has 1 is equal to 2 chance of being chosen after the second step. For the induction step, assume that every one of n has an equal chance 1 is equal to n of being the chosen item. When the n first item arrives, it replaces whatever item had been chosen with probability 1 is equal to do n p1p. The previously chosen item is therefore retained with probability n is equal to do n p1p. Multiplying, we find that each previous item has a chance of being kept of n is equal to do n p1p is 1 is equal to n power of 1 by 4. 1 is equal to rho n p1p. So every one of the np1 items has an equal chance of being chosen outside of the stream processing environment. Why should this substell algorithm be used? Typically, everything is in memory and a program can do two passes. The first pass counts the number of items when the second pass chooses one at random. Suppose that the selection is computationally intensive. For example, only numbers that are prime are candidates to be chosen randomly. It would be insufficient to check for primality in the first pass of count. Choose a random number of k. The repeat the preliminary checking when counting through to find the kth item. A program might catch the primes identified in the first pass, but then the program is more complicated. Virtual memory aware heap. We present an implementation for the classical binary heap that works better with modern memory systems. Binary heaps are used in priority queues and the heap sort algorithm. Typically, heads are implemented with an array. A node at index I has child nodes at indexes 2i and 2i plus 1, and a parent node at index I by 2. With one based indexing, the problem is that for large heaps, almost every level ends up in a different virtual memory pages. The traversing from the root to a leaf causes a page fault for almost every level and occupies a significant amount of cache. The B heap is a modification that allocates significant subtrees in a single page. Typically, pages are large enough to hold subtrees with a dozen levels. Thus, the number of page fault is reduced up to an order of magnitude, using far fewer entries in the cache and page tables. Other variants such as cacheables algorithms, im- implicit KV heap, compacting an array. Finally, we present a parallel algorithm with multiple core machines being the norms for personal computers, phones, and even embedded devices. The community must be aware of the opportunities of parallel programming. Cloud and distributed computing makes the need even more urgent. The problem we consider is compacting an array, that is, copy of non-zero entries from one array to another array. A simple serial algorithm accomplishes this in QNP time. Can we accomplish this faster using parallel processing with a minimum of complications? Wishkin gives a parallel algorithm 18 to compact an array in Q log NP time. Assuming Q NP hardware, the output is a shared array A of size n. The output is a shared array B, assumed to be big enough. To help explain the algorithm, we present the XMTC code for it as a reference. The keyword spawn creates one thread for each index in. Each thread runs its own copy of the code in the body of span. Is a thread number. The interesting part is PS, which is the prefix sum operation. Here it automatically copies the value of the shared variable dest to E, then increments dest. It is equivalent to the following two assignments occurring simultaneously, where the primed variables represent the new values. Such each thread gets a value of dest and increment dest. Each thread gets a unique index of B. These indexes for B are assigned from 0 to 1 less than the number of non-zero entries. Software technology. Each intermediate thread passes the dest it receives from above to its left subtree and dest to the right subtree. All the threads receive distant values in Q log NP time, which they use as their E value. Thus, every value from A is put in a unique place in B. Each dest value is unique since the least value in a right subtree is just beyond the highest value in the left subtree. Although compacting an array is not common, prefix sum is used in sorting. Wishkin gives several other commonly used algorithms which can be easily parallelized. Conclusion. In this presentation, I have learnt about new constraints and opportunities in computing, such as high parallel, cloud, and energy aware computation, can lead to novel, elegant, broadly applicable algorithms and data structures. We call for renewed interest in and resource for research of basic algorithms and data structures. Programs should be taught some cost aware data structure and algorithm to understand the benefits of and need for such improvements. More to point, such data structures and algorithms must be conveniently available for standard libraries as standard model algorithm currently are. Busy professionals seldom invest extra time or effort to obtain the best tool for a job if an adequate tool is already at hand.